areas. Okay, so area, if you are doing this in terms of x, you're doing top minus bottom. If you're doing it in terms of y, you're doing right minus left. They are not going to tell you which one to do. But from the picture, I can see right here. Can I do right minus left for this picture? No, because I don't have a right function and a left function, right? So this has to be a top minus bottom. Over here, can I do top minus bottom? No, because I need right minus left on this one. So they're not going to tell you which one to do, but you can see from the picture which one you need to do. There are some problems, like, was it the third FRQ, where you could do it either way. And in which case, as long as you do it correctly, it doesn't matter for that. So we have here, I'm going to call this purple graph, I'm going to call it f of x. And I'm going to call this green graph g of x. So if you are finding area between curves, just about zoomed in too much. Need a little room to write here. If you're finding area between curves here, you are simply going to do the integral from x-axis is where your limits come from, a to b, of top function. Which one's the top function here? G of x minus bottom function, which is f of x dx. Everything's in terms of x. Limits come from the x-axis. No squares, no pi's, none of that, just top minus bottom for those. Okay, so these are the easier ones, except for they are also the ones they may ask you to solve all the way down to the answer more often, right? Because they're not as complex as the next ones that you'll see. If you're in terms of y, so let's call this red graph right here. I realize yours is not colored, but they don't give me color copies. I'm going to call it f of y. Remember, that needs to be something like x equals y minus 4, right? It's got to be everything in terms of y. And then the blue graph, I'm going to call it g of y there. So when you find this area, you're going to integrate the right, which is g of y, minus the left side, which is f of y dy. All of your equations here have to have y's in them. It's like y squared plus 3 minus 2y minus 7 or something like that, right? Everything's y's right there. Right. So like these equations need to be x equals, we'll put something there, it's not going to be right, but y plus 3. And this might be x equals 9 minus y squared, right? It's going to be x equals equations. Whereas here, it might be something like y equals sine of x plus 2. And this might be y equals x squared plus 7, right? I'm just making things up. Those aren't the right equations. But you got y equals equations here if you're doing it in terms of x. You got x equals equations if you're doing it in terms of y. And that'll be true throughout. The limits here must come from the y-axis, so it's your lowest point C to your highest point D. Yes?
Can you explain the perpendicular parallel thing one more time? Like how you know if it's in terms of y or x?
We'll get to it.
Okay.
For these, it's the picture. So if it's just asking for area, you have to kind of figure out which one can I do.
Okay.
You generally, like, look at your equations. If they're if they're in terms of x, if they're like y equals x squared plus 7, you're hoping you can do top minus bottom so you don't have to change anything.
Could they just say it's this and then force you to change it?
Yeah, they could give you one that has to be done right minus left, and then you have to change it. But usually it's a little more straightforward on this section. This is usually like at the beginning of these types of problems. Yeah.
Would this be like for and right here multiple choice? Like these? Well, I guess they don't say.
Yeah. Yeah. Like, usually if you see these on the FRQ, it's towards the beginning of the FRQ, right? Like, it's like all of these that I gave you last night, I think the first step was finding an area, right? So it's just top minus bottom or right minus left, integrate either with your x coordinates or your y coordinates. So that's usually like at the beginning. Then they're probably going to ask you some volume problems. And they might be rotations and they might be cross sections. Okay? So my next section here is what we do if we have cross sections. Okay? So it's going to say something, it'll say the phrase cross section in the problem. Okay? So for cross sections, you are integrating whatever area formula you have for the shape of the cross section. Okay? So if it is a square, your area is side squared. I'm going to draw a little tiny out to the side here. That is because you'd have a little square and the area would be S times S, right? For rectangles, you're going to, you have a couple different things they might give you with rectangles. They might say rectangle with a height of 7 or rectangle with a height of 4, right? They just tell you what the height of the rectangle is. So B right here represents those numbers, right? Then your area, the base is S, and the height is whatever number they give you for that B. So it might be 4 times S or 3 times S, 7 times S. That should say times instead of time right there, but I was really working on this last minute there because I think it's kind of important. So rectangle with a height, that is C times the base, right? So not just the height is C, not like the height is 3. The height is 3 times the base. That will look like this. On all your rectangles, your base is S. Your height would be C times S, or 3 times S, or 4 times S, whatever that number is, right? C just represents a number here. So it's going to be C times S squared is your area formula there. Isosceles right triangle with one leg that lies in the base. That means that the right triangle's laying like this, and this side right here is S. What does it mean for a triangle to be isosceles? 2 sides are the same, so this other leg right here is also S. So the formula for the area of that triangle is 1/2 base times height, which is 1/2 S times S, which is 1/2 S squared. Equilateral triangles, I'm not going to go through and show you how to get that one. It's more complicated. You're not going to see it today on the FRQ. I can't promise you won't see it on the actual exam, but it's square root of 3/4 S squared there. Semicircles are 1/2 pi r squared. Now, here's what you got to be careful with on this. Your semicircle, this bottom side right here is going to be S. So, R has to equal half of whatever S is. Right, so where all these other problems we're drawing that little line and calling it S, on this one you still draw the line, still call it S, but for the formula you got to cut it in half, right, because it's radius. Yes, S is like a diameter. Yes, good. Note right here, this is important for you. For cross sections, semicircles are the only time you should see pi, because we've done so many rotations, and every rotation has pi, right? Pi r squared, pi r squared, pi r squared for all your rotations. So we just start putting pi's everywhere. Cross sections, you will not have a pi unless you're doing semicircles, right? No pi's unless you're doing semicircles. Okay, and then you might get something like this. The area of the cross section is given by a of x equals 3x squared plus sine x, or the one that we did yesterday, it said like a of x equals sine of 1/2 x, or something like that, right? If they give you an area formula, just integrate that area formula. Like, you don't do a S, you don't set anything else up, you just integrate that area formula using the limits from either the x or the y axis, depending on whether the function gives you x's or y's. Yeah.
So like with the brackets come out, Like for these?
If it asks you to solve it all the way, like let's say we had, like for example, right here, you would need to integrate, well, get a pen. You would integrate from, let's say it's 0 to 2 of 3x squared plus sine x dx. Right? I don't know if that's the right limits, but we would have something like that. So you will integrate that, so you'll have just x to the third, because when you divide out front by 3, you get 1. And what do we get when we integrate sine? Negative cosine x, and then you'd have a bracket over here, 0 to 2. So this is where you've integrated. You have to do 2 cubed minus cosine 2 minus 0 cubed minus cosine 0 here. And then you can stop after that. Technically, I don't like to let you guys leave cosine values in there either. My example here, you'd have to, because cosine 2 is not a unit circle value. You can do cosine of 0, which is actually 1, which is why you need to be careful of not just calling that second part 1 here. But unless you need to use it for something else, you could stop at that point. But you have to, so like when the bracket is there, you have to go that one more step to plug the numbers in, and then you can stop after that.
How would you know when to use the unit? Like when you get it, it's like sine of 2x.
Yes.
Yeah.
So if I was like sine of 2x instead of just sine of x, then we would need a u on this one. Okay. So cross-section examples. All right. Now I can't do every single cross-section example. But they could either be in terms of x or in terms of y. If they are in terms of x, they will say cross-sections perpendicular to the x-axis. I've seen a couple questions that say parallel to the y-axis, which would mean perpendicular to the x-axis. But most of them will say perpendicular to the x-axis. So if you see perpendicular to the x-axis, that tells you it's a dx problem. You're doing everything in terms of x's. So what you're going to do is you're going to go over here to, no matter what the shape is, you're going to go over here to the figure, and you're going to draw yourself a vertical strip on that base, right? Unlike the rotations, we don't go all the way to what we're rotating around because we're not rotating, right? We're just across the base, perpendicular to the x-axis, so it's going to be vertical. We're going to call that our S. And so if this, like let's say the red right here is f of x, and let's call the blue graph right there, we'll call it g of x. So no matter what your shape is, right, doesn't matter what shape it is, unless they just give you an area formula, then you would integrate without worrying about a s. But if they give you squares, rectangles, triangles, semicircles, whatever, you're going to say that your S equals, you're going to do top of that line, which is f of x, minus bottom of that line, which is g of x. Okay. Now, depending on the picture, it might not be f minus g. It might be g minus f. You just have to look at the picture to tell. Then, what you do from there depends on whether you have squares, rectangles, triangles, semicircles, whatever. So, like if you have squares, a of x would equal s squared. So, for this problem, a of x would equal f of x minus g of x squared. And you would integrate f of x minus g of x squared dx. What would the limits be here? A to b. They come from that x-axis there. If I had the same picture, but they said semicircles, well, I know the area for a semicircle is 1/2 times pi r squared. Now, you're going to have to go an extra step here because r is not s, right? What is r? Half of s. So, r is 1/2 of f of x minus g of x there. So you would plug that in. And then you got a lot going on here, but especially if it's just a setup problem, you could just integrate from a to b, the 1/2 pi 1/2 f of x minus g, actually, of x. I do think I got one more parentheses there. These actually might be a little bit easier when you do have numbers than when you have that f of x, because I got tons of parentheses going on here, because you could always like distribute that 1/2. So if it's actual numbers, sometimes distributed in that 1/2, like you got like 2x plus 4x squared. When you distribute, it's a simpler function. Yes?
So for cross sections, this x-axis, it's perpendicular to the x-axis, it's always going to be the top minus bottom.
Yes.
Okay.
Yeah, this is always going to be top minus bottom.
And that will be dx all the time.
Dx, yes. Okay, everybody good there? You got similar things going on whenever you have perpendicular, oh, it's not the highlighter, perpendicular to the y-axis. That is a dy problem, meaning that we would need to call like this function, I'm going to call the red f of y right here, and I'm going to call the blue g of y. Again, meaning that we got like x equals the square root of y plus 1, or x equals y minus 2, right? Whenever we got f of y, that's a x equals function. Again, if you're perpendicular to the x-axis, you're coming in here, you're doing a horizontal strip, and you're calling that S. So cross-section problems, you always have an S, right? And if it's horizontal, like we have here, S is going to equal right minus left. So f of y minus g of y. And so then it depends on what shape they have asked you for. So like if they say, let's do ones we haven't done, isosceles triangle with leg in base. Sometimes I have to think of the picture. That means like where we got that S right there, we're going to be making a right triangle. Both sides will be S, right? It's going to be 1/2 base times height, 1/2 S times S. So our A of Y is going to equal 1/2 S squared. And so we'll plug in our S. We got 1/2 f of y minus g of y squared. And then we set up our integral from C to D. Make sure you're pulling those limits from the y-axis. 1/2 f of y minus g of y squared. Be really careful right here. Make sure you've got this second parentheses right here. If you are using like f of x and g of x notation, it's really easy to leave off that second parentheses, which means only the y is being squared instead of the whole thing. Another thing you might want to do is use brackets right there instead. Like you could put a bracket here and a bracket here so that you make sure you close that bracket to just make sure. Because if you're missing that last parentheses and it's just a setup problem, you're probably not going to get it just because of that missing parentheses. So be really careful with those. sometimes it's like actual number, like it's 2x minus square root of x or something there. And so in a way that's almost easier to plug in than the f of g or f of y or whatever. What if we had rectangle with height 2 times the base? So if we think of drawing that rectangle, the base is s, right? On everything the base is s. What would the height of that be? 2s. And so our a of y would be 2s squared. We'd plug in our s, f of y minus g of y squared. And then to get area, to get volume, we would integrate that formula. 2f of y minus g of y. Let's bracket again. Off bracket's better. dy, forgot my dy over here. And then c to d. Try to put your dx's and your dy's. It helps you remember this is a y problem. I'm looking at the y-axis. Try to put it. If you forget it, you can probably still get credit for the problem. There. Okay, those are cross sections. Cross sections have s's. S's go across the base, whatever that base is, right? Top minus bottom, left minus right for that s, and I'm sorry, right minus left. Said that backwards. And you plug it into an area formula. You should not see pi on these unless it's a semicircle. Okay, then let's talk about disk method. Disk is when you don't have a hole in the middle. Okay, so if you have no hole, you only need a capital R of X, or it could be capital R of Y, right? You do not need an inside and an outside radius, because the capital R and the lowercase r is the outside and the hole, right? So if there's no hole, you only need a capital R. So if I name, I'm gonna call this green function right here. Actually, this particular green function, it would be like I guess it's x equals a, right? It's not a function. It's not f of x. It's x equals a. And then the red function, let's just call it f of x, right there. So I'm thinking about taking this. I'm rotating around the x-axis. So if I'm rotating around the x-axis, it's a dx problem, right? Dx problem right here. My little piece is going to be vertical. Notice, although these are different than cross sections, it's different than the S, I still have a vertical piece, right? If you're doing dx, you're going to have like a little vertical. Your radius is vertical or your S is vertical, right? And so this would be my capital R. And we're going to do R of X equals top minus bottom. But if you're rotating around the x-axis, it is y equals 0 every time for these, right? So like if you're rotating around the x-axis and it doesn't have a hole. So we're doing capital R of X is f of X minus 0. So capital R of X is just f of X. Here. And so every rotation problem, you're integrating pi r squared, right? So we're doing pi integral f of X, I like this better, squared dx. Limits come from the x-axis. It's a to b here.
So even if there's a hole, do you also square that?
So I've got some examples coming up for a hole.
Okay.
If there is a hole, but you do also square for the hole because it's still rotation. But if there's a hole, there'll be the capital R and the lowercase r. Yeah, but both of those still get squared. Everything you integrate is pi r squared if you're rotating around the axis. All right, if we're rotating around the y-axis, then y-axis tells us that it's a dy problem, right? Which means that function right there, that needs to be f of y. So it's something like x equals sine y, not y equals sine x. If it's not solved for y and for x, you've got to solve it for x, right? So you're thinking about doing a horizontal strip on these. Anything that's a dy problem, your little strip is horizontal. Whether it's the r or the s, it's horizontal. And you do right minus left. And if it's the y-axis, the left is 0, right? The left is going to be x equals 0. So like our radius here will be capital R of x is, right side is whatever f of y is. Ooh, I messed up having that should be a y right there. Everything's y's. F of y minus the left side of that line is just 0. So, capital R of y, for this particular case, is just f of y. And so I integrate pi integral of f of y squared, put a dy over here. This will be from c to d. Those limits come from the y-axis. Okay, let's do a couple more. These are still no hole. Okay, still no hole. You're rotating around a horizontal line, but this time that horizontal line is not the x-axis. But on this one, I'm going to tell you to rotate around. This is going to be y equals 2 right here. And it doesn't have to necessarily be 2, but I just put a number in there because I was thinking that the letters were getting out of control if I made that a C. So I think it's a little easier for you to see whenever it's a number. So if we're rotating around the line y equals 2, our graph touches the line we're rotating around everywhere. So you're not going to have a hole whenever you rotate this. So if there's no hole, that tells you only need a capital R, right? So again, horizontal line is like the x-axis. That tells you your dx problem. Also tells you that your little strip that you're rotating around, your capital R, is vertical. So you will do top minus bottom. So like for this problem, capital R of x is going to equal, well, let's first name these functions. Let's call this one right here f of x. And we actually don't need to name the bottom one because it's already named. It's y equals 2. So top, we're hitting the blue line, which is called f of x. What do we subtract for the bottom? What do we hit at the bottom? 2. And since we don't have a hole in this graph, that's all we need. And so whenever you do your volume, you're going to do pi integral from still a to b. Those limits come from the x-axis. Whatever your capital R is, f of x minus 2 squared dx. Okay, does that help? All right, vertical line. That tells you dy. Right here. Let's say that we're rotating around here. This is going to be x equals 2 right here. Let's rotate around this vertical line, x equals 2. So if you're rotating around that vertical line, our shaded area touches that line everywhere. When you rotate this, you're going to get like a cone shape. It's not going to have a hole in the middle of it. So here, our capital R of x needs to be horizontal. Let's call that red line, we'll call it f of y. And so capital R of y is going to be right. What do we hit on the right? The red line, which is f of y, minus left. What do we hit on the left? 2. Right? And once you get your radius set up, pi r squared, integrate it, right? So pi integral from of f of y minus 2 squared dy. Actually, on this one, I put some numbers in here. I was about to put c to d, but I put numbers on this one. What's our lower limit? 0, 2, 8. Okay, y coordinates that we're looking at there for our limits. Okay, we got 4 more. Maybe we can get them in before my time limit is up. All right. The washer method is for when you have a hole in the middle. This just means you got to do volume of the outside. Let's write that down.
Is there like a verbiage or like word that will say that shows like this, or you like kind of like just look at that?
You have to see these from the graph. Yeah. So
Like on this other one, it'll say rotate around the horizontal.
right. This is gonna sound just like the 4 that we just did, right? So they're gonna say, like, region R is bounded by, rotate R around the line x equals 2. They are not gonna tell you whether or not there's a hole or not. So you have to see from the picture, oh look, I touched that line, I'm rotating around everywhere. There's not gonna be a hole. So you kind of have to visualize it a little bit. So like right here, if I rotate this around the x-axis, right here, there's going to be a hole, right? So you have to be able to see, oh, there's a hole. So if there is a hole, you're doing volume of outside minus volume of inside. You need capital R of x and lowercase r of x for your hole. So let's name these functions. Let's call this red one right here. Let's call it f of x. Let's call the blue one g of x. And as far as which one goes first, f or g, it all depends on the picture, right? I'm just naming things and then put them in there. It's not that f always goes first or g always goes first. Look at your picture. So here, around x-axis, that's a dx problem. We need to go vertically, but it's important on these that you pay attention to the line that you're rotating around. I mean, I really didn't highlight it much over here, but I was doing it also. Like, let's go back. Here's the line we were rotating around. Here's the line we were rotating around, right? Up here, x-axis is what we were rotating around. Y-axis is what we were rotating around. Okay, notice that my capital R goes from that line I'm rotating around to the outside of the figure. Line I'm rotating around, outside of the figure. Line I'm rotating around, outside of the figure. Line I'm rotating around, outside of the figure. So we might even make ourselves a note. Radius, capital R of x, and r of x must touch the line you are rotating around. Because what a lot of kids do wrong here is they'll call this, don't write this down, this is not right. They'll call this capital R right here. And that is not what we do, right? So what we need, and that would be like an S, and that would be cross sections, and that is not what we're doing here, right? So line we're rotating around here is the x-axis. So for capital R, you go from the line you're rotating around, the x-axis, to whichever function is furthest away. That's where you get your capital R. So, rotation line to outside function. So, here, capital R of x here is going to be top, f of x, minus bottom, which is 0. And for x-axis, that second part will always be 0. Okay, and if you mess this up and do bottom minus top on these, it's not the end of the world, because pi r squared is going to square that, and you'll have wrong signs, but squaring it makes everything positive, so you can still get it right, even if you kind of mix it. Probably none, because it's still mathematically correct there. I don't think they will take off for that. I've never graded one of these there, so yeah, so I don't think they take off as long as it's mathematically correct. But it's better to do top minus bottom or right minus left for the device. Lowercase r of x, rotation line to inside function. So here, that's going to be g of x minus 0. When you're doing x-axis, both of those numbers are going to be 0, right? So, for your volume, make these pictures kind of big, zoom out a little bit. For your volume, you are going to do pi integral of capital R of x, which in this case is just f of x squared. Limits come from the x-axis, a to b, minus pi integral from a to b of g of x squared. And for today, like, there's no need to put those together unless you just like to. You can, yeah, that'd be fine if you just want to put it there. Okay, we're running out of time. Let's keep going. This is f of y. Let's call that red one f of y. We're going to say this right here is going to be x equals 2. And we are rotating around the y-axis. That tells us the problem is a dy problem. I'm going to highlight that line that I'm rotating around. So, capital R, there's definitely going to be a hole here, right? Because my solid area, my shaded area does not touch the line I'm rotating around. So, line you're rotating around to the outside. That's capital R. For this one, capital R of y is going to equal f of y minus 0. Again, don't have to have the 0, but it's okay if you do. Here, outside, line you're rotating around to the inside, that's your lowercase r. For this problem, that is, what is our, like, right side hit right there? 2 minus 0. Now, this is not always a number right here, but since that's just a horizontal line, it is a number on this. You see, like on the last problem, both functions were actual, like, functions. This one's just a vertical line right here. So, my volume is pi integral from C to D of capital R of X, which is just f of y squared dy, minus pi integral from C to D R of y squared dy. Oh, I shouldn't have used that R. I mean, you could, because you've already defined it up there, but let's just use the 2 right there. Okay, we are like basically out of time, but let's do these last 2 really, really quickly, okay? So, same idea, but the line you're rotating around has changed right here. If I'm rotating around, rotate around y equals 10. So, capital R, line you're rotating around to outside, that's capital R. Right, capital R here, oh, gotta name them. Let's call this one, this is f of x in red. Call this g of x in blue. So, like for this one, capital R of x would be, I go, blue line is g of x. No, I'm doing it backwards. You could get away with this.
Is it y? Like, it's R y or no? It's R x.
It's R of x because it's a horizontal line. Any horizontal line is going to be a horizontal line is a dx. But what I did backwards is I should do top minus bottom of this. So I should do 10 minus g of x. Good news there is if you do what I just did and get those backwards, when you put it in and it's squared, it's not going to make a difference. So it'll be okay. Then you will go, line you're rotating around to the inside, the closest function, that's your lowercase r. R of x would be 10 minus f of x on this one. So we would have pi integral from a to b of 10 minus g of x squared minus pi integral from a to b of 10 minus f of x squared. And last one, let's call this one f of y. This orange line is x equals 2. We are going to rotate around x equals negative 3. So this line right here is what we're rotating around. So, going to have a hole because you don't touch the line you're rotating around. Line you're rotating around to the outside, that's capital R. So capital R of y is going to be right minus left, f of y minus negative 3, which if you want to, you could say f of y plus 3. Lowercase r, line you're rotating around to the inside. So lowercase r of y is 2 minus negative 3, which is just going to be 5. So volume is pi integral from c to d of f of y plus 3 squared dy minus pi integral from c to d of 5 squared.